Hello dear students, and today I welcome you on our fourth lecture in our fourth module. And today we are going to talk about basic AC theory. And also I have that after this lecture everything will be clear for you. First of all, guys, let's determine what is alternating current or DC. Most students of electricity begin their study with what is known as direct current or DC, which is electricity flowing in a constant direction and or possessing a voltage with constant polarity. DC is a kind of electricity made by a battery with defined positive and negative terminals, or the kind of charge generated by rubbing certain types of materials against each other. As useful and as easily to understand as AC is, it is not like only kind of electricity in use. Certain sources of electricity, exactly most notably rotary electromechanical generators, naturally produced voltages alternating in polarity, reversing positive and negative over time. Either is a voltage switching polarity or as a current switching direction back and forth. This kind of electricity is known as alternating current or IC. Figure 1.1, whereas the familiar battery symbol is used as a generic symbol for any DC voltage source. This circle with a wavy line inside is a generic symbol for any AC voltage source. One might wonder why another would bother with such a thing as AC. This is true that in some cases AC holds no particular advantage over direction of current, irrelevant, so long as there is enough voltage and current to the load to produce the desired heat or power dissipation. However, with AC it is possible to build electric generators, motors and power distribution systems that are far more efficient than DC. And so we find AC used predominantly across the world in higher power applications. To expand the details of why this is so, a bit of background knowledge about AC is necessary. Also, guys, in this picture you can see the examples of direct and alternating current. From the left side, this is our direct current or DC. From the right side, you can see the example of our alternating current or AC. Also, guys, if machine is constructed to rotate a magnetic field around a set of stationary wire coils with the turning of a stop, AC voltage will be produced across the wire coils as the shaft is rotated in accordance with Faraday's law of electromagnetic induction. This is the basic operating principle of an AC generator, also known as an alternator. And also you can see the example of this in figure 1.2. Notice how the polarity of the voltage across the wire coils reverses as the opposite poles of the rotating magnet pass by. Connected to a load, this reversing voltage polarity will create reversing current direction in the circuit. The faster the alternator's shaft is turned, the faster the magnetic will spin, resulting in an alternating voltage and current that switch directions more often in a given amount of time. While DC generators work on the same general principle of electromagnetic induction, their construction is not as simple as the AC counterparts. With a DC generator, the coil of wire is mounted in a shaft where the magnet is on the AC alternator, and electrical connectors are made for this spinning coil via stationary carbon or brushes, contracting copper strips on the rotating shaft. All this is necessary to switch the coil, changing output polarity to the external circuit, so the external circuit sees a constant polarity. And also, guys, this is our one more picture about DC generator operations. Also, here we have some steps exactly for step 1. This is our load. Step 2, step 3, and step 4. The generator shown above will produce 2 pulses of voltage per revolution of the shaft, both pulses in the same direction or polarity. In order for a DC generator to produce constant voltage rather than brief pulses of voltage once every 1.5 revolution, there are multiple sets of coils making internet contact with the brushes. The diagram shown above is a bit more simplified than what you would see in real life. The problems involved with making and breaking electrical contact with a moving coil should be obvious: sparkling and heat, especially if the shaft of the generator is revolving at high speed. If the atmosphere surrounding the machine contains flammable or explosive vapors, the practical problems of the spark-producing brushes contact are even greater. An AC generator alternator does not require brushes and cumulators to work, and so is immune to these problems experienced by DC generations. For today, guys, that's all. After this lecture, I attached for you some tasks. Please do them, and I wish you good luck. See you soon.